In September 1859, telegraph operators disconnected their batteries and discovered that some lines could still send messages. Electricity was entering the wires from the planet itself. Elsewhere, equipment sparked, operators received shocks, and papers reportedly caught fire. Above them, red and green auroras glowed so brightly that people mistook night for dawn. The source was not on Earth. Hours earlier, 2 astronomers had watched a flash erupt from the sun. The event that followed became the most famous solar storm in recorded history and the first warning that a technological civilization could be hit by weather from space. This is Pip's Fact Orbit. One familiar fact, and a much stranger story. In the middle of the 19th century, the telegraph was the nervous system of a rapidly connecting world. Long metal wires carried coded electrical pulses between cities and across countries. Operators used batteries, keys, and electromagnets to turn those pulses into messages. Newspapers, railways, governments, and businesses had begun to depend on it. The sun, meanwhile, was still mysterious. Astronomers knew that dark sunspots appeared and changed, and they had discovered an approximately 11-year cycle. They did not yet understand solar flares, plasma, the solar wind, or the enormous magnetic fields that shape space around Earth. On September 1, 1859, English astronomer Richard Carrington was projecting a filtered image of the sun onto a screen and sketching a large sunspot group. He did not stare through an unfiltered telescope. Suddenly, 2 patches of intense white light appeared inside the group. Carrington briefly left to find another witness. When he returned, the lights had faded. Richard Hodgson, another English observer, independently saw the same phenomenon. Their reports became the first recorded observations of a solar flare in visible white light. Carrington did not instantly announce a modern theory. He cautiously noted the timing and later compared it with the magnetic disturbance that followed. Earth had already experienced strong auroral activity on August 28 and 29. Then, roughly 17 to 18 hours after the September 1 flare, magnetic instruments lurched and a far larger disturbance began. A normal coronal mass ejection often takes several days to reach Earth. This one, or a sequence of eruptions that cleared the path ahead of it, traveled extraordinarily quickly. A solar flare and a coronal mass ejection are related but different. A flare is a burst of electromagnetic radiation from magnetic energy released in the solar atmosphere. Its light can reach Earth in about 8 minutes. A coronal mass ejection, or CME, is a vast cloud of magnetized plasma thrown into space. When a fast, Earth-directed CME arrives with the right magnetic orientation, it can transfer energy into Earth's magnetosphere. That energy drives currents high in the atmosphere and changes Earth's magnetic field. A changing magnetic field can induce voltage in long conductors on the ground. This is electromagnetic induction, the same basic principle used in generators and transformers. In 1859, telegraph wires stretching for kilometers were excellent unintended antennas. Reports came from North America and Europe. Telegraph signals became garbled or failed. Sparks jumped at equipment. Some operators received shocks, and small fires were reported. At certain stations, the induced current was so steady that operators disconnected their batteries and continued sending messages using what they called the auroral current. One celebrated exchange occurred between Boston and Portland, Maine. Operators reportedly removed their battery power and continued a conversation using the current produced by the Aurora. They even discussed the strange source powering their instruments. The story survives because the telegraph was both a victim and a detector. Its faults recorded the storm across a continental network long before anyone could place scientific instruments in space. Telegraph technology also made the disruption unusually visible. A compass needle moving strangely might interest an observatory, but a commercial message failing affected schedules, money, and public information. Operators compared notes across distant stations, revealing that the problem was not a local battery or broken wire. A planetary disturbance had appeared simultaneously inside machines separated by hundreds or thousands of kilometers. That strange success should not be misunderstood. The solar storm did not provide clean, free electricity to an entire network. Most of the effect was disruptive and dangerous, but on a few lines, operators could exploit the current temporarily. Space weather had turned infrastructure built for one electrical source into a circuit powered by changes in Earth's magnetic environment. The sky delivered the most visible evidence. Auroras were reported at unusually low latitudes, including the Caribbean and Central America. Some accounts described brilliant red light. People could reportedly read newspapers by it. In places where auroras were unfamiliar, fire companies were called because observers thought a distant blaze was reflecting from the sky. Aurora does not mean solar material is burning in our atmosphere. Charged particles guided by Earth's magnetic field collide with oxygen and nitrogen high above the surface. Those atoms and molecules release light at characteristic colors. During an extreme geomagnetic storm, the auroral oval expands far beyond its usual polar region. The name Carrington event came later, and it can hide Hodgson's independent observation and the fact that the storm was a sequence, not one neat explosion. Modern scientists also debate exactly how intense it was. There was no satellite measuring the solar wind, and today's standard geomagnetic indices did not yet exist. Researchers reconstruct the storm from magnetometer traces, auroral locations, newspapers, ship logs, and telegraph reports. For that reason, claims that it was precisely an X-class number or that it had one exact modern storm index should be treated cautiously. It was unquestionably extreme and is often described as the largest geomagnetic storm in recorded history, but the numerical ranking depends on how incomplete 19th century measurements are interpreted. The telegraph failure revealed a principle that still matters. Long conductors collect geomagnetically induced currents. Today, high-voltage transmission lines, pipelines, undersea cables, rail signaling, radio systems, satellites, and navigation services create many more paths for space weather to affect society. In March 1989, a much smaller geomagnetic storm contributed to the collapse of Quebec's power grid. Protective systems tripped, and millions of people lost electricity for about 9 hours. In July 2012, spacecraft observed an extremely powerful solar eruption that crossed Earth's orbit after our planet had moved away from the impact path. It became a famous near miss. A Carrington-scale storm today would not simply turn off the internet forever. Effects would vary by latitude, ground geology, grid design, satellite orbit, the storm's duration, and the direction of its magnetic field. Possible consequences include transformer stress, voltage control problems, satellite anomalies, increased atmospheric drag, radio blackouts, and degraded GPS accuracy. The most consequential component is not fully known until the plasma is close to Earth. NOAA and other spacecraft monitor the solar wind about 1.5 million kilometers upstream. That can provide roughly 15 to 45 minutes of warning about the magnetic orientation that determines how strongly a CME will couple with Earth's field. Earlier solar observations can provide longer notice that something is coming, but not a perfect forecast of its impact. Orientation matters, because magnetic fields can connect and transfer energy efficiently when the arriving field points opposite to part of Earth's field. A very fast cloud is alarming, but speed alone does not determine the ground impact. This is why a dramatic solar image cannot, by itself, predict which transformer will overheat or which satellite will have trouble. Forecasts combine solar imaging, physics models, upstream measurements, and the vulnerabilities of specific systems. Modern engineering also changes the comparison. With 1859, many devices are hardened, monitored, or designed with protective relays, but today's networks are vastly larger and more interconnected. A system can be more resilient in one component and more dependent overall. The sensible conclusion is neither complacency nor panic. Rare solar storms deserve the same kind of planning used for earthquakes, floods, and other low-frequency hazards. Grid operators can change configurations, reduce vulnerable loads, delay maintenance, and prepare response teams. Satellite operators can place spacecraft in safer modes and postpone risky maneuvers. Airlines and radio users can adapt routes or frequencies. Forecasting does not stop the storm, but it can turn surprise into preparation. There is another reason not to treat 1859 as a once-in-all-history anomaly. The sun continues to produce powerful eruptions. Most miss Earth, arrive with less dangerous magnetic orientation, or are absorbed by systems designed to tolerate disturbance. Smaller storms regularly create aurora and temporary technical effects. Extreme events are rare, but the 2012 eruption showed that solar physics did not retire with the telegraph. Carrington's sketch survives. A dark cluster of sunspots with small white regions marking the flash he saw. It looks modest compared with modern images from solar observatories, yet that drawing connects three systems that people in 1859 had never linked so clearly: the sun, Earth's magnetic field, and human technology. So did a solar storm really make telegraphs run without batteries? On some lines, yes, briefly. A changing geomagnetic field induced enough current and long wires for operators to send messages after disconnecting their normal power. The same process caused shocks, sparks, garbled signals, and fires elsewhere. The lesson was not free energy. It was that our machines do not sit outside nature. Build a network large enough, and even a storm 93 million miles away can reach into the circuit.